Hello and welcome to Critical Care Concepts, where we discuss the core concepts behind all things critical care. My name is Anirban Bhattacharjee, and the topic for today's video is ventricular pressure volume loops. This is what a typical pressure volume loop looks like. It has the instantaneous volume of the ventricular chamber plotted in x-axis and the corresponding pressure plotted in y-axis in real time during an entire cardiac cycle. Pressure volume loops are measured by putting a PV catheter inside ventricular chamber by transaortic or transeptal approach. The basic principles is that there are 12 electrodes on the catheter and the proximal and distal electrodes generate an electrical field. The device measures the volume of the LV cavity by dividing it into imaginary cylindrical segments around each electrodes. The volume of each of these segments is given by this equation, where I is the current, rho is the resistance of the blood, d is the distance between adjacent electrodes, and Vi is the potential difference drop across adjacent electrodes. We already know how much current has been generated and the distance between two adjacent electrodes. This is what the catheter measures, the resistance of the blood and the voltage drop across the two electrodes. The resistance of the blood is eventually estimated by the volumetric calibration of the catheter. This is what the computer derives. Now the total volume of the LV cavity is the segmental volume times the number of segments. How does the catheter know how many segments are inside the LV cavity and how many are in the aorta? By seeing the individual pressure volume loops of the segments. As you can see here, the segment 7 has a figure of 8 in the pressure volume loop, which is usually seen when the segment is in the aorta. Therefore, the first 6 segments are in the LV cavity and their summation of their volume gives us the total volume of the LV cavity. Simultaneous with volume measurement, there is a pressure sensor on the catheter which measures the instantaneous pressure inside the LV cavity. Now let us draw a pressure volume loop. For that we will start with the ventricular filling. So the ventricular filling starts with when the mitral valve opens and ends when the mitral valve closes. So this is the diastolic filling phase of the ventricle. After that, the ventricle goes into systole, where initially the aortic valve is closed and therefore only the pressure rises inside the ventricle. However, there is no change in the volume. This continues till the aortic valve opens, and this phase is the isovolumetric contraction. Once the aortic valve opens, the ventricle ejects into the left ventricular outflow tract, and thereby the volume of the LV cavity decreases. This left ventricular ejection continues till the aortic valve closes and the ventricle goes into diastole. So initially, with the mitral valve closed, the ventricle relaxes without any change in its volume, which is known as the isovolumetric relaxation phase. If we join the end systolic points of the pressure volume loops of sequential beats while changing the preload by vena cava occlusion, we get a regression line that is called end systolic pressure volume relationship. It is linear and is load independent, unlike end diastolic pressure volume relationship. The slope of this line is end systolic elastance and it is a measure of the contractility of the ventricle. The parameter V100 is the end systolic volume that corresponds to an end systolic pressure of 100 mm mercury. This parameter is correlated inversely with contractility. Therefore, with increased contractility, the V100 value decreases, and with increased contractility, the end systolic pressure volume relationship is shifted towards left. Here we can see the too contractile state of the heart, probably because of administration of an inotrope. So we can see as the contractility increases, the end systolic pressure volume relationship is shifted towards left, and the slope of the end systolic pressure volume relationship, which is the end systolic elastance, is increased. How the end diastolic pressure changes with changes in ventricular diastolic volume is understood by this curve called ventricular end diastolic pressure volume relationship. This relationship, unlike end systolic pressure volume relationship, is non-linear, as we can see from this slide. The slope of the curve corresponds to the elastance or stiffness of the ventricle. Now, what is elastance? It is the resistance offered by any elastic structure to change in its conformation. It is mathematically a ratio of the change in pressure by the change in the volume of the LV cavity. Compliance, on the other hand, is the inverse of elastance and is equal to the ratio of change in ventricular volume by change in ventricular pressure. This diagram shows how the slope of the end diastolic pressure volume relation changes with the elastance of the heart. So, in patients with heart failure with preserved ejection fractions who predominantly have diastolic dysfunction, the curve is shifted towards left and the slope has increased. Whereas for a remodeled heart in ischemic cardiomyopathy, the elastance decreases and thereby the curve is shifted towards right with the slope has decreased. Now we can understand it quantitatively by measuring the V30 parameter. The V30 is the volume inside the ventricle, which corresponds to a diastolic pressure of 30 millimeter mercury. Therefore, with increasing V30, the elastance decreases. There are other parameters that can be calculated or measured from the pressure volume loop. That these are the stroke volume, the ejection fraction, which is stroke volume divided by the end diastolic volume, the left ventricular end diastolic volume and pressure, the systolic pressure and the end systolic volume and end systolic pressure. Typically, the end systolic pressure is slightly lower than the systolic pressure, and the relationship is somewhat around 0.9 into systolic pressure is the end systolic pressure. As the left ventricular cavity empties its stroke volume into the arterial system, the pressure in the arterial system rises up to end systolic pressure in a linear manner. The slope of this rise gives us the arterial elastance. The relation between end systolic elastance and arterial elastance is extremely vital for optimal functioning of the ventricle, and this relationship is known as the ventriculo-arterial coupling. We will have a separate discussion on ventriculo-arterial coupling in a separate video. If we decrease the arterial elastance slope by administration of a vasodilator, we can see that the pressure volume loop changes and the end systolic pressure and both systolic blood pressure decreases. So this is how the vasodilator leads to reduction in blood pressure by decreasing the arterial elastance. If we compare the pressure volume loop of a normal heart with that of a heart failure patient with reduced ejection fraction, we can see that the end systolic pressure volume relationship has shifted towards right and its slope, which signifies end systolic elastance, has decreased. We can also see that the ventricle has become much more compliant, as evident by the shifting of the end diastolic pressure volume relationship towards right with decrease in its slope. We can also appreciate that the end diastolic volume has now increased. So for the same stroke volume, the end diastolic volume is higher in a case of heart failure with reduced ejection fraction, thereby reducing the ejection fraction, which is nothing but stroke volume divided by the end diastolic volume. We can estimate the lithotropic property of the heart by seeing how fast the LV relaxes during isovolumetric relaxation. As in this case, we can see that the time taken for the LV to relax during isovolumetric relaxation is increased, thereby suggesting early diastolic dysfunction due to impaired relaxation. Another important utility of a pressure volume loop is the ability to understand the myocardial work and myocardial oxygen demand from the area of the pressure volume loop. So what is the area of pressure volume loop? If we multiply pressure and volume, it eventually translates to the product of force and displacement, as we can see in the slide, which is nothing but the work. So in work here in this case is the work done by the heart or your myocardium. If we imagine our ventricle to be a closed structure which is contracting rhythmically with every systole without leading to a ejection of blood, then we will find this kind of a curve where the pressure increases with each cardiac cycle, however the volume does not change. In this case, the area in the pressure volume loop is stored as the potential energy in the ventricular wall without leading to any stroke work. However, in case of a normally ejecting ventricle, a part of this work translates into the stroke work, that is the energy spent in generating the stroke volume, and the rest of it is the internal work which is converted to potential energy or dissipated as heat. Now the efficiency of the myocardium is the ratio of the stroke work divided by the total work. In other words, an efficient myocardium will be able to convert at least 60% of its total work into generating stroke volume. A failing myocardium will produce less stroke work for the total work it does. In summary, pressure volume analysis has multiple clinical applications, as we can see in this slide. But for an intensivist, the most important utility of a pressure volume analysis is giving us a conceptual framework to understand the interplay of preload, afterload, contractility and diastolic function of the heart, as well as to understand bioenergetics of the heart and ventricular arterial coupling. Thank you.